Good morning, everybody. This talk will be on cosmic ray acceleration driven by turbulent magnetic reconnection, and I will discuss mainly the large scales of the process, in MAGD scales, I mean, but we will also make comparisons with the smaller scales. And I should thank the collaborators of this project that this list includes the students, postdocs, and also colleagues from everywhere, and some of them are in this audience. So I think this community knows that particle acceleration by reconnection is regarded as important at also beyond the solar system, and in all magnetically dominated regions, from systems like stellar coronae, relativistic jets, accretion flows around compact sources, pulsar nebula, and even in the more diffuse intra-cluster and interstellar medium. So let me start with a brief overview on theoretical grounds and earlier numerical simulation results. Reconnection in MAGD astrophysical flows is believed to be mainly driven by turbulence. This because turbulent flows violate flux freezing, so magnetic field lines suffer Richardson diffusion, as nicely demonstrated, and as a consequence, they unavoidably reconnect. And also as a consequence, the plasma does not stay in the same magnetic field line, but diffuses, enabling reconnection diffusion that has a strong dependence on the Alfvénic Mach number. And also, so turbulence drives reconnection, and it drives fast reconnection. Why is that so? Because turbulence allows for the wandering of the magnetic field lines, there is slippage, and this implies many simultaneous events of reconnection, which makes reconnection fast and a substantial fraction of the alpha velocity, and also independent on the tiny, small scale resistivity of the system, or it's independent of the inverse of the Lundquist number here represented. Actually, it depends on the injection scales, on the parameters of the turbulence at the injection scales as predicted by Lazar and Vishniak. And this theory has been thoroughly tested through three-dimensional resistive MAGD simulations, and more recently up to Lundquist numbers up to 10 to 6. And these more recent simulations, like this one, for instance, have demonstrated the dominance of turbulent reconnection over Terry mode reconnection. How do we accelerate particles in reconnection sites? So our understanding for a while has been that particles trapped in current sheets, in magnetic flux of opposite polarity, will bounce back and forth and undergo head-on collisions with magnetic fluctuations within these converging magnetic fluxes, or in other words, they suffer a Fermi-like process just like in shocks. So they will they will be accelerated by shrinking magnetic fluctuations. And this process predicts that after each round trip, particles have a net energy growth that is proportional to the reconnection velocity over c, which means that this is a first-order process. And if the reconnection velocity is constant, this implies an exponential growth in time of the energy of the particles after several bouncing back and forth. And in this three-dimensional simulation, we injected a test particle. We have a three-dimensional current sheet with turbulence embedded in it to make reconnection naturally fast. And we see a test particle here, the trajectory in green, and this particle really have an exponential growth in energy while it suffer head-on collisions with the background magnetic fluctuations. So in this case, we see that the effective accelerating electric field of the particles is probed by the ideal electric field of the background fluctuations minus V cross B. And the resistive electric field is actually negligible because eta is small, and this can be important only at the very small time resistive scales. Besides the Fermi acceleration, particles also suffer drift acceleration. When their larval radius becomes larger than the accelerating reconnection layers, the particles undergo they undergo drift acceleration in the varying magnetic fields, the non-reconnected fields. And of course, this process increases mainly the perpendicular momentum of the particles, while this one mainly the parallel momentum. And we have tested this successfully by means of numerical simulations like this one, for instance, where we injected 10,000 particles inside the three-dimensional reconnection domain with the turbulence making fast reconnection. And what we see with that these particles, this is the histogram evolution of the kinetic energy evolution of the distribution of particles as a function of time. And we see that the particles, once they enter in the acceleration region, they are accelerated by the reconnection structures from the resistive to the up to the injection scale of the turbulence. And beyond this point, the particles escape the acceleration region beyond the injection scales of the reconnecting structures, and they suffer further acceleration by a slower rate by drift. In this log-log diagram, we really see that the Fermi process is nearly exponential, and the particles develop a power law spectrum. We repeated the same experiment, but now removing the large scale magnetic fields of opposite polarity and injected pure turbulence in initially homogeneous magnetic field. And what we found essentially the same, that the particles still undergo the reconnection acceleration within the turbulent system up to the injection scales of the turbulence, and then suffer slower drift. Just that in this case, we have less particles being accelerated. Well, I have also tested more recently the acceleration in situ, particle acceleration in relativistic jets in the magnetically dominated regions of a relativistic jet, where turbulence was driven by kink instability. And then we injected test particles in a nearly steady state turbulent jet structure. And again, we see the particles undergoing Fermi acceleration and accelerating their energies up to several orders of magnitude of their rest mass, meaning for background magnetic fields between 0.1 and 10, we have found that particles can be accelerated up to ultra high energies, and so they have more than enough energy to produce TV, gamma rays, and neutrinos. Of course, this happened within a few hundred hours over scales of between 0.01 and 0.1 parsecs for these simulations. Well, and what about the acceleration time in these processes? In the turbulent current sheets, we do see Fermi and drift acceleration, and the acceleration time in both the turbulent current sheet and the turbulent jet during the Fermi regime have a little dependence with the energy, only with this power between 0.1 and 0.2, which means that the process is really nearly exponential. And in the drift, we have a nearly linear dependence with the energy, so it's a slower process and with a stronger dependence on the energy. So how do these results compare to particle acceleration by reconnection at the kinetic scales? Well, I should say that these are two parallel worlds of research that hardly talk to each other, right? Hardly interact. But I should say that at the kinetic scales are probed mainly by particle in cell simulations, peak simulations, and these probe only microscopic scales of the process. I mean scales between 10 to minus 10 and 10 to minus 70 orders of magnitude smaller than the real astrophysical scales of these systems, depending on the system, while MAGD probes the macroscopic astrophysical scales. So both approaches are complementary and should be studied and investigated together. Fast reconnection driven is essentially by tearing mode instability, the plasmoid-like instability, and has been mainly studied in 2 dimensions in kinetic, while fast reconnection is driven by turbulence in 3D, intrinsically 3D MAGD reconnection, where turbulence is driven by natural instabilities like Kelvin-Helmholtz, MRI, kink, instability, as I showed, and even tearing instability. The reconnection velocity in kinetic depends essentially, primarily on the resistivity, and reconnection does not depend on resistivity in MAGD, but on the scales, the injection scales of the turbulence, as I mentioned before. Particle acceleration here up to 1,000, because it only probes the kinetic scales of the process, so particles are accelerated at most a few thousand times their rest mass, while in here they can be accelerated up to 10 times this, as I've shown in the experiments before. The dominant electric field is generally the resistive electric field, while in this case is the non-resistive minus V cross B of the background structures. It could be the non-ideal also in some peak experiments. More recently, 3-dimensional peak simulations have detected really only in 2023, they detected for the first time in this experiments by Zhang, Giannius, and Cironi, drift acceleration. And there is no consensus in this community still what might be the predominant mechanism, either Fermi or drift, or drift acceleration. Actually, they claim that is the drift that is ruling or determining the power law spectrum, while in MAGD we have known for more than a decade that both processes occur, with Fermi acceleration dominating up to the injection scales of the turbulence in pretty high energies, and drift acceleration in energies above this one. And the power law spectrum is determined, obviously, because of this, by both Fermi and drift acceleration. So, it's interesting to compare 3-dimensional experiments of particle acceleration in MAGD with 3D peak accelerations in pure turbulence. So I've shown this before, where we have Fermi and drift, but if we compare with this very nice, more recent experiment by Luca Commisso and Cironi, we see essentially that in spite of the difference in scales, both the spectrum and the energy growth are pretty similar. And I would dare to say that what they are saying here, in spite of the fact that they may have a different interpretation, but what I would say is that here they are really seeing the Fermi process of particles being accelerated in the reconnecting turbulent structures of the turbulent flow in all scales of the turbulence, and then when they escape these, they are further accelerate at a smaller rate by drifting the non-reconnected fields. Okay, how do we know that particles are accelerated mainly back in the MAGD simulations? How we know that the particles are mainly accelerated in the reconnection sites? Because we have done several mathematical exercises. So, for instance, my former postdoc has developed an algorithm that can find mathematically the reconnection sites in a large scale system, turbulent system like the jet, for instance. And here, for instance, these circles are all sites of reconnection, and are sites where density, current density is a maximum, and we can compute all the characteristics of these reconnection sheets. And in this image, if we zoom into this in one of these regions, we see these nice current sheets. And when we compute the reconnection velocity, we see that it grows and saturates with the time, along with the growth of the turbulence, the kink-driven turbulence in the system. And it saturates to values, to average values of this, with peaks of this, and this is a key point for efficient particle acceleration. And this is what we did. So in these nearly steady state turbulent environments, we injected test particles, and we got this result that I have described before. But in order to understand better what happens in the transition from the small to large scales, we have more recently explored, in attempts to explore kinetic and the MAGD, this transition, we have performed peak relativistic MAGD simulations using the same setup for the relativistic jet in the magnetically dominated region as before. But in this case, we allow the particles to evolve with the growing, with the background evolution, along with the background evolution of the jet. And by the way, these green dots are the particles embedded in the system. And as the turbulence, as the kink instability develops turbulence, so the particles start suffering before the development of the turbulence. They suffer some curvature drift, and then Fermi, and finally some drift. And here we see the accelerated particles in red after a while, and we see that the sites where they are accelerated nicely are comparable to the fast reconnection sites, coincide, right? Are connected. And here we see the energy growth of these particles. They experience initially some curvature drift, and we have identified this also in the steady state turbulent simulations with test particles. Then they undergo reconnection acceleration in the Fermi regime, and we see that they have started doing some drift, but we see that the particles here are accelerated just for a while, because they are allowed to evolve only for the dynamical time of the jet, which corresponds for the particles just 1 hour. So I'm running out of time. The particles develop a power law spectrum as well as time goes by. And I do not have time to explain the details of this, but we have compared the acceleration time that we get from the simulations with recent theoretical predictions made by Xu and Lazarian. And I cannot explain to you the details, but what we find is that when we do this comparison, directly computing the acceleration time from the reconnection current sheets, and compare with the acceleration time that we got from the test particle acceleration, we see that they are comparable. And really, so we are really seeing that the particles are being accelerated in the fast reconnection sites. To conclude, I would just briefly tell you that we have been doing applications of reconnection acceleration to probe very high energy phenomena associated to relativistic jets and accretion flows in agents. So, for instance, we have probed the variability in gamma rays of this very well studied Blazer Markarian 4021. I don't have the time to explain this, but if you can ask me in the questions. We have also probed this spectral energy distribution of the famous Texas Blazer, where we were able to see both by reconnection acceleration, the peak in neutrino, the the neutrino peak, the neutrino flare, followed 2 weeks later by the spike in gamma rays. Also, we have been exploring for quite a while reconnection acceleration in accretion flows, evolving from analytical and more recently to simulations of fast reconnection driven by MRI turbulence. And motivated by these findings, we have performed GRMADD simulations combined with radiative transfer and cosmic ray cascading simulations in order to probe the spectrum of Sagittarius A, for instance. And we have predicted that Sagittarius can be a pavotron to be tested, in forthcoming years by the new experiments in gamma ray, CTA, and SWGO. So I would just tell you with this slide that I would like to see this barrier between the two scales to be removed so that we can study better and give a better understanding of what's going on particle acceleration by magnetic reconnection in all scales. I should say that we should perform and exercise caution when making direct extrapolations from peak simulations at kinetic scales to large scales without considering MADD results. So thank you, and I leave my to-dos here.
Thanks. So questions? First one from Greg.
Hello. Okay. Do you see any dependence on the plasma beta in your simulations with the effectiveness of this acceleration by reconnection?
You mean the ratio between thermal pressure and magnetic pressure?
Yes.
Okay. This we did not explore yet on particle acceleration, but we have been exploring these effects on reconnection, on the driving of fast reconnection by turbulence. And what we see is that the dependence on beta there is some when you increase beta by a factor of 10, but it's a small dependence.
So what are the beta values for the simulations that you actually have?
Mm-hmm. Oh, I beg your pardon?
I mean, you showed a whole bunch of simulation results. What are the plasma beta values for those simulations?
Oh, yeah. Uh-huh. You mean those simulations? What is
you showed a whole bunch of stuff, and there's got to be a beta for the plasma, right?
I don't. You mean in the reconnection sheet simulations?
Any of the simulations? Yeah. Like, are they low, are they high beta? Are they beta 1? I'm just trying to get a sense of where you are in parameter space.
No, they are beta around 1 and smaller than 1.
Okay.
Right.
Thank you.
Yeah, I think a lot of her simulations are parameterized with sigma, that the sigma order unity. So essentially, a sigma goes up, beta goes down. I assume that probably you are in a parameter regime with beta 0.1 or lower. Just look into them.
Exactly. And yes, the sigma effect is an interesting one because in those simulations of jets, for instance, we are simulating exactly the transition region between magnetically dominated and kinetically dominated, where emission, the gamma ray emission and the higher come out.
Yeah, in the meantime, if that we wait other questions, I have my question. You have some images of a section of a jet with some position of particles tracked during the simulation. I wanted to know, do you emphasize those particles in positions that are related to the particle acceleration or particles that have high Lorentz factor so that they may have been accelerated? I think before you had another slide where you were looking to locations of acceleration.
This one,
but exactly, are those particles the particles that have the highest Lorentz factor or the particles that are being accelerated at the moment of the snapshot?
Okay, you have.
So the derivative of the Lorentz factor versus high Lorentz factor.
Yeah, this is an interesting point because, okay, here we have the distribution of the highest accelerated particles. When you look for, individual particles, how they jump, they go up and down, it's sometimes difficult to see because they have just left a reconnection site, and then they are going this, and then they start again, and then they come back. But yeah, we do see this let's say this dependence with the energy, or in other words, with gamma.
So exactly, but so in these plots, I didn't know what is emphasized for those particles, if they are already energized, and so essentially they are transported somewhere else, far from the location of the acceleration, or they have been energized in the moment in that location.
Yeah, here, this map, of course, you have superposition of all the events between a given ratio of energies that are given here. But yeah, you have both. You have particles that have just, left, and particles that already, that are still in that process.
I see. Are there any, another question for Alex? Yes.
I would like to ask you to quantify, if possible, the relative role of the Fermi acceleration, first order Fermi acceleration, second order Fermi acceleration, and the drift acceleration. I would like, for example, to know if you did not have the time to show the Pevatron, what is happening, and for what is happening in the jets. Do you see differences? What's the reason for these differences?
Okay. So if you go to pure turbulence, right, probably the particles are getting more second order acceleration, but this is still Fermi acceleration in this regime. And the interesting point is that the particles really are maintain being accelerated by Fermi in this exponential regime, while they are interacting with the turbulent reconnected structures. And this is from the resistive scale, that is tiny, to the injection scale, right? This is no matter experiment, either if we are in the jet, or if we are here in this pure turbulent environment, or in the turbulent reconnection sheet, we have the same effect, right? Drift occurs only when the particles no longer see the reconnecting layers, and these reconnecting layers are as big as the injection scales of the turbulence, right? And so drift occurs after the saturation energy that occurs. Oh, Sasha, okay. So this saturation, as you know, occurs only when the particles, their Larmor radius becomes bigger than these injection scales, right? That are the size of the largest reconnection structures. Betatron acceleration responds for the, and then beyond this, they suffer drift in the gradient, in the varying space-varying magnetic fields, large-scale, non-reconnecting fields. So we have both effects, and we do see clearly that there is a change in regime. Here, the same. Here, it's first order. Why is that so? Because we have this large-scale current sheet or flux stub, converging flux stub. So particles essentially undergo head-on collisions. While in this case, particles may also suffer receding collisions, or in other words, they may gain and lose energy. So the efficiency of this process is more second order like, but still it's Fermi.
One final question from Sasha.
Thank you for the wonderful talk. I'm curious if you ever see transition to plasmoid-dominated reconnection, and if you do, does it make a difference for particle acceleration in your simulations?
Okay, this is a very important point because, plasmoid-like reconnection, these magnetic islands exist only in 2 dimensions, right? In 2D. The plasmoids, the islands, only in 2D. In 3 dimensions, these are actually nothing but cross-sections of reconnecting flux stubs. And particle acceleration is three-dimensional, right, in nature. So when you do reconnection experiments where you drive fast reconnection by tearing in MAGD simulations, even in 3D MAGD simulations, you may have tearing instability breaking the current sheets. Eventually, this tearing instability evolves into turbulence. So it achieves a saturation in the reconnection velocity that is literally independent of the reconnection scales, and so is essentially turbulent-driven reconnection. So you can drive in spontaneous turbulence reconnection out of the tearing or plasmoid-like instability.
Thanks again.
Sorry. Thank you.